Okay, everyone, this is Emily at Quasi. It's about 3 o'clock, so I think we should go ahead and get started with this webinar because we have quite a lot to go over today. Today, we have some program updates on the NFIE. Some information has changed since the last webinar that we will go over. And then we also are going to have some presentations. Fernando Salas is going to kind of do a NFIE in a nutshell recap. We also have a presentation on team science from Emily Reed at USGS. And then we'll also hear some student presentations from students that are currently working on NFIE projects. So with that, I'm going to turn it over to Al Veloki, who is the Quasi Chair of the Board of Directors, to go over some of the NFIE program updates that we have.
Okay, thanks, Emily. Hello, everyone. As you probably all know, Quasi is coordinating this the NFIE activity on behalf of the academic community, and wanted to just update some of the logistics about how the program is going to run in the application form. So let's see here. So after the last webinar, there was an issue that came up, and it's basically because the National Water Center is an operational federal facility, only U.S. citizens can be accommodated as residents working inside the National Water Center. So we wanted to have both U.S. citizens and international students participate and have the same type of experience. And so our solution is that the University of Alabama is going to host the international participants on site, and they would still be working very collaboratively with the U.S. citizens who are inside the water data center. So this led to the creation of 3 program categories, which is going to allow eligibility for both citizens and non-citizens. And the other thing that we've done is that we've opened it up now to prospective graduate students. So senior undergraduates are eligible to apply, and postdocs are also eligible. So I wanted to just go through the 3 different program categories. The first is the NFIE Summer Institute Fellows Program. This is the one that's only open to U.S. citizens, and it's 7-week residence in Tuscaloosa, June 1st through July 17th. And you're going to be working in, in the National Water Center primarily. The second program is what we call the NFIE Summer Institute Resident Scholars Program. This is the one that's open to international students. You'd still be in residence in Tuscaloosa, June 1st through July 17th. You'd be working at the University of Alabama, but only have limited access to the National Water Center. But we still anticipate that the teams will be fully integrated. Both members from the Resident Scholars Program and the Resident Fellows Program will be integrated in the same teams and would work together. And then the third category is the Visiting Scholars Program, which is open to U.S. citizens and international students. This is where you come to Tuscaloosa for the boot camp and capstone events at the beginning and the end of the institute, Summer Institute, and you work under your guidance of a mentor at your home institution, and you'll be participating in weekly webinars. For the application, we're going to update the application, so we would request that you wait until tomorrow until we get the updated application form. There will be one application for all 3 programs, and you would indicate on the application form which program you're applying to. And it's the same information that we mentioned in the previous webinar, CV, transcript, statement of intent, or project description, and a letter of support from your advisor. Combine everything into a single PDF and submit it by the closing date, which is the end of this month. And if you have any questions, you can, as always, email Emily Clark. And just to remind you here of important dates and deadlines, again, the last day of February is when all the applications have to be submitted. By March 31st, this quasi-steering committee will decide and issue their decisions to all the applicants, and then during April and May, the selected applicants are going to be formed into project teams, and then June 1st is the kickoff. So that's all the information I have, and again, if you have any questions, please contact Emily, and Quasi is willing to help in any way it can. Thank you.
Okay, thank you very much. So my name is Fernando Salas, and I'm a PhD student at the University of Texas at Austin. And myself and Joseph Gutenson, who you'll hear from in a little bit, will actually be at the Water Center throughout the Summer Institute. And we're going to help the people that come down there in various different capacities, helping evolve ideas, helping execute those ideas, and interfacing with different agencies and things like that. So I want to give a quick overview of the NFIE for those who haven't been on the previous webinars, and explain a little bit of the modeling that we've been doing, and then we'll proceed to hear from a few different people who've been working on different projects related to the NFIE. So essentially the goal of the experiment is to connect national scale weather and hydrology that's being computed and performed by our federal agencies to local scale emergency response, and essentially demonstrate that forecasting done at that national scale can have an impact in how we respond to flooding events. So we're building a national scale hydrologic model, and we're going to build this upon what we call the NFIE Geo, which essentially is a geospatial framework for hydrology, and this is based in large part on the NHD Plus data set, which is essentially a river network or a drainage. It's just a framework for how the drainage system of our country operates or works. So we have divided the country up into 2.67 million catchments, and each of those catchments have a corresponding river segment, and those river segments are all connected and drain to the various different coasts. So to kind of organize the work for NFIE, we have a framework that we've come up with. We have the NFIE Geo, which is the framework, the geospatial framework part. We have the NFIE Hydro, which is National High Spatial Resolution Hydrologic Models. We have NFIE River, which is the channel information and the real-time flood inundation mapping. And then we have NFIE Response, which is the actual planning for different flooding events. And all this is within a NFIE services framework, because to operate this in real time, we have a bunch of different services that we're relying on for the communicating different types of information. So this is an example of NFIE Geo for Travis County in Texas, and again, we see all the catchments represented here. The catchments have the corresponding river segments or river reaches, and then we have the stream gauges and the locations of reservoirs. And the idea here is for the NFIE Geo is to construct, or put together all the geospatial information that we need to be able to model or put together a hydrologic model for the entire country. So how things drain where the flow is interrupted by reservoirs and things like that. So for NFIE Hydro, essentially we have weather models, and we take the outputs from those weather models and feed them into land surface models. From there, we take the runoff and feed them into large-scale river routing models or channel routing models. And then what we would like to do is be able to produce ensemble forecasts at all the NHD Plus river segments. So, we have ensemble predictions starting with the atmosphere and feed all those different predictions down through the land surface model and then through the river network, so that we have an ensemble solution of all the possible flows, outcomes that we could have at a particular river segment. And again, we're connecting the land surface to atmosphere outputs to the river reaches themselves through the NHD Plus catchments, which we've put together through the NFIE Geo data sets. Now, assuming that if we don't have, in some areas we won't have very accurate channel information, what we can do is, with the flow forecast that we have at the stream level, we can intersect the catchments with the flood hazard layers that come from FEMA. And then we can color code those resulting polygons in a way similar that has been done by the Weather Service. So, the purple would represent heavy impact on structures and roads. Red would be some impact on structures. Orange and yellow, would be reduced risk, essentially, as you move down in categories. So, again, if we don't have any extensive channel information, what we can do is come up with these polygons and color them based on the flows that we're getting from the NFIE hydro modeling. Now, if we do have extensive channel information, then what we can do is within the NFIE river component of the interoperability experiment is essentially use the hydraulic models that we have. We can construct rating curves based on those, and then also if we have LiDAR data, integrate that information, and then we can go from flow and actually compute water level and stage heights, and then intersect that with the land surface to actually get flood inundation polygons. So just depending on the level of information that we have, that's what we can focus our work on. Now, again, to summarize, this is pretty transformative for the nation, because right now what the Weather Service does is, we have flood forecasts at about 3,600 locations across the U.S., and what we're trying to accomplish is to have flood forecasts at about 2.67 million locations across the country. So that's 700 times greater or more dense than the system that we currently have. And what we want to show through this interoperability experiment is how, we can take state-of-the-art technology and science now to, to produce, hopefully an operational model into the future that the Weather Service and other agencies could use. Again, the NFIE response part here is working with the local emergency responders to use the data that we produce and see how we can come up with a wide area plan for flood forecasting. Okay, real quickly on the NFIE hydro stuff, we're using the rapid river routing model, which is a large-scale routing model that works on that uses the Muskingum method to route flow through the entire network. Again, we're using the catchments to aggregate runoff from the land surface models, and then we're also specifying areas where we have reservoirs, and then using flood forecasts for the reservoir releases to route the flows at those areas down through the river network. So that's just an example of the routing model at large scale that we're using, but we can use others as well. We're using the WRF Hydro Framework to do the land surface modeling. These slides will be posted so you can look at this in more detail later. And then we're using the high resolution rapid refresh model as the atmospheric forcing to drive the land surface models themselves. And this is an hourly model that's run every hour. It gives a 15-hour forecast, and it's a 3-kilometer resolution. So that's just a summary of some of the models that we'll be using, and we're going to put this all together in an automated fashion so that we're computing flows, ensemble flows, every 3 hours or so for the entire country. So now we're going to listen to a little bit Emily Reed, who's at the USGS, and she's going to talk a little bit about team science, since we'll have a lot of different graduate students and postdocs and at the Water Center working together.
Great, thanks, Fernando. So if it's not obvious to all of you already, the NFIE is most certainly an interdisciplinary experiment. And just taking a look here at the research questions and the training objectives for the NFIE Summer Institute, you can see that the disciplines represented range from hydrology to emergency response to information technology and computer science. So the work that comes out of this is definitely going to be interdisciplinary, and with that come certain challenges and also opportunities. So today what I'm going to do is give you some definitions of interdisciplinarity and some of the other associated jargon. I'll talk a little bit about some of the challenges that exist for interdisciplinary research, and then also briefly touch on processes that can help interdisciplinary teams be more effective. So just to start with some definitions here, in traditional disciplinary collaborations, scientists from a single discipline come together and they're guided by the traditions, the methods, traditions, and kind of perspectives of that particular discipline. In multidisciplinary collaborations, there are scientists that come together from different disciplines to address a particular question that tends to be rooted just in a single discipline. So although there might be different methods or interpretive standards from the various disciplines employed, typically the interpretation is just going to be done within a single discipline. In contrast, interdisciplinary collaborations are more integrated than the previous two. So you, again, have people coming together from different disciplines. The research questions may span spatial scales and temporal scales, which indeed they do in this case. And interdisciplinary collaborations tend to be more integrated in that the collaborators are in some cases borrowing methods from other disciplines, and the outcomes may lead to new questions and new methodologies. And then finally, there are transdisciplinary collaborations, and these come out of problems that are actually unique and can't be captured within an existing disciplinary framework. So in this case, there are methods and perspectives that are generated that are new, and this is really almost like a new discipline may be created out of a transdisciplinary collaboration. So those are just some definitions for you to start with. And if you think about these different levels of integration, or from disciplinary to transdisciplinary, the processes by which teams work together may be different, and that's what's depicted here in this figure. So in particular, for more integrated interdisciplinary research, you've got team members coming together, bringing their own specific expertise. Teams need to meet frequently and have a high level of communication about the team goals, but also individuals' objectives. And then there's also a lot of sharing that takes place, so sharing of responsibility, decision-making, data, and credit. So the challenges that come along with interdisciplinarity are listed here. Some of them are listed here. So there's that level of integration, which can, the expectations for integration can vary depending on the discipline from which a scientist is coming. There may be linguistic and conceptual divides. So for example, there's some terminology that is used across disciplines, but depending on the specific discipline, those terms may mean different things, and this can lead to miscommunications and inefficiencies. The way that evidence is validated most certainly varies across disciplines. This can be a source of, it can be a challenge in interdisciplinary collaborations. And then there are a number of other kind of more philosophical things that can become an issue when working with people from different disciplines. So before entering an interdisciplinary collaboration, some questions that participants should personally consider, but also collaborative groups should consider, are listed here. So related to motivation, is the research basic or is it more applied? What kind of methodology will be used? And what's the most appropriate for the particular goals of the interdisciplinary collaboration? What is the type and amount of evidence that's required for knowledge? I think that's one that definitely varies across disciplines, and it's important to consider. And then some questions on objectivity, the role of values in scientific research, and then a question about reductionism and emergence. So team science is a process that is particularly well suited for interdisciplinary collaborations, although it can also be used in single discipline collaborations. Team science is a collaborative approach to scientific inquiry where you've got teams of investigators coming together to meet a particular scientific goal or research goal. There's also the science of team science, and that's actually a field of study about how people work together in scientific teams. And many of the materials that I've drawn from for this presentation today are from scholars of the science of team science. So at a very high level, what does team science require? It requires communication, trust, setting expectations, and dealing with conflict. So the national academies note that at the heart of interdisciplinarity is communication, so just connecting with people across disciplines. Trust is very important in that without trusting relationships, people you consider to be collaborators may turn into competitors, and this can undermine the forward progress of a research team. So having that trust there is very important. Setting expectations, I think that I probably don't need to talk too much about that. That's definitely important for multi-person work or for teamwork. And then finally, having a toolkit for dealing with conflict is very important because conflict's definitely present in all collaborations to some level, but the ability to manage it effectively is not something that is necessarily taught in graduate programs and in disciplinary training. So that can be another great tool to bring to team science. So what does a successful interdisciplinary scientific team look like? So these teams will have a very good, be very effective at assigning and negotiating roles and responsibilities. So it's very clear who is responsible for what. To be able to discuss, recognize, and also respect differences in worldviews that may arise from the different disciplinary traditions. That's something that's very important. Again, this ability to manage conflict. And then finally, the last one here is kind of related to trust, and that's the ability to share laughter and social interactions outside of research that really is what forms the glue that can hold a team together. So what teams there's kind of a tension that exists in effective scientific teams in that they're balancing meeting the research objectives and the immediate goals with maintaining this group cohesion that can be very important for ongoing collaborations. So in conversations that I've had with Fernando and others, I've had a little bit of an opportunity to talk and think about, you know, what kind of processes could help support really great interdisciplinary outcomes at this NFIE Summer Institute. And I do have to say that I think a lot of the parts are already in place for this. A couple of ideas shown here are the idea of kind of interspersing the technical training with training on team science best practices, facilitative skills, and then also opportunities for the relationship development between scientists and students that are participating. In addition to this, the research projects you know, should be attainable within the time period, and they should also be adequately supported, and I know that there's plans for this in place. Frequent communication both within research teams and across research teams is also something that's very important and beneficial. And then finally, just taking a flexible approach to the Summer Institute experiment. And a way to do this is just to kind of check in and consider changing course, well, not necessarily changing course, but adapting the approach as needed based on the experience of the participants. So finally, I'd just like to point you to the Global Lake Ecological Observatory Network Fellowship Program. I spent 2 years doing a postdoc on this program, which is funded by the NSF Macrosystems Biology program. And this is a program that has many kind of similar, not research goals, but similar goals in terms of interdisciplinarity as the NFIE Summer Institute does. And if you're interested in seeing workshop agendas, some of the technical and team science training materials, and then some of the scientific research descriptions, you're more than welcome to check that out. But just in a nutshell, this was a 2-year fellowship program, and students from across the world came together to build up both technical and kind of the softer human network skills that are required for interdisciplinary research. And they had really strong scientific and outcomes as well. So with that, I'm just going to acknowledge my references here and pass the baton to Joseph.
Thanks, Emily. Hi, everybody. This is Joseph Goodinson. I'm a PhD student here at the University of Alabama. I have been working in the area of hydraulics and hydrology probably since August. I had mainly geared my research towards drinking water, but we've geared up at the university here. We've geared up our interest with NFIE and with the National Water Center here on campus. And so I'm going to cover some of the projects that we have started to develop here, as well as ones that have been ongoing for some time. Just to start, I had developed a couple, so I became interested in this, and I began doing research on it, and I found a couple of holes that were pretty gaping. One of those, and this is probably one of the more obvious holes that I found, was that with the existing nationwide coverage of terrestrial topography, this doesn't necessarily always include even larger streams. In this case, we have a location on the Alabama River west of Montgomery, Alabama, the state capital. At this location, we have the Robert L. Henry Lock and Dam, and what has happened is in HECRAS, or HECGeoRAS rather, I created a inundation model, and at this location you can see that I have a discontinuous depth grid. The reason being, after a little bit of investigation, was that the elevation just above the dam was actually at 150 feet where the reservoir was supposed to be. And so in this case, we ended up with a location where this is actually the deepest part of the river in this particular area. It actually wasn't showing up as an inundation. So again, this is more of a duh kind of thing, but this is one of the areas that have proven to be problematic. So we have to learn how we can use high definition topographic and bathymetric data to measure inundation. Another area that I've found, this is the city of Montgomery, and in this I've portrayed the May 7th, 2009 flooding event, which was, it wasn't a large-scale biblical type of flood, but it was a small flood nonetheless. It did about $7 million worth of damage. And here on this map I have four important layers. The pink dots represent georeference locations of damage. Along with that, we have in the checkered area there, which is kind of hard to see, the special flood hazard area where anyone with a federally backed mortgage has to purchase flood insurance. I also have the national flood hazard layer that Fernando alluded to earlier, along with the annual flood risk zone. And what we see here is that between those three specified areas on this map, only about 16% of the points that were recorded by the city of Montgomery for damage fell in one of those three areas. So again, we have a lot of issues with urban hydrology in this case, but if we zoom in just a little bit, we see that at the catchment scale, if we can improve inundation in those areas, we're going to grab some of these points and be able to predict more accurately at the neighborhood, at the local scale. And so again, this is just a good demonstration of what NFIE is gearing towards. And so here at the University of Alabama, we've basically a class taught by my advisor, Dr. Ernest, and a class in Texas taught by Dr. Maidment. We have been thinking up different ideas that could be useful using the NFIE framework. In this slide, I've organized everything in terms of the different components of NFIE and what we at the University of Alabama are working on. For hydro, that's where a lot of our more developed projects are existing right now, particularly with VIC. One of the postdoctoral researchers here, Dr. Obadilla, has done a lot of research with the VIC model, and he actually completed a national scale VIC model. And he's scaled that down to the Mobile area river system here in Alabama as well, and so he's gotten some really good results with that. We're also interested in comparing things. We're interested in comparing the models that have been developed for the NFIE hydro section, comparing those with what we have and what we could create. There's a model called WMB Plus, I think. Is it water balance? WBM Plus, rather. Sorry. That is another tool that we can investigate its application within the NFIE hydro framework. Within NFIE RIFR, I'm sorry?
Joseph, we're a little bit behind on time, so if you could only get 2 or 3 more minutes, and that would be perfect.
Okay. So anyway, guys, What we've also got going on here are ways of developing channel morphology. Again, Fernando alluded to one of the issues is that we don't have developed bathymetric data, and so we're looking into that as well. We're also looking into another one of our particular strong suits is rule-based decision support systems. We've done a lot of work with drinking water systems in the past, and we're hoping to continue with that in the future with flooding. One of the projects in particular that students here at the university have put together is the investigating the influence of land use and land cover on flood inundation. In phase one of this project, they are planning on investigating the role that current land use has on flooding and predicted land use has on flooding. The model's built on the different climate change scenarios as well as the different urban expansion models that are used. And they're basically planning on using the different land covers, throwing those into, I believe, VIC, and seeing how that affects the flooding. Here are just a couple of graphics that they are wanting to demonstrate. Here we have the basic, the centroids of the different grid cells in these particular watersheds. I think this is the Russian River in California. And at the grid cells, they demonstrate color-coded flood frequency. And so their proposal is to take this hydrologic model, compare that with the different land use, land cover, in the two different scenarios, see how that impacts flooding for different recurrence intervals, and then feed that actually into an economic consequence model to investigate the economic impacts. Skipping ahead, this is the idea with channel estimation. We were looking into using the various power function relationships that were developed, basically estimating channel geometry based on the concept of hydraulic geometry that was developed back in the 50s, I do believe. And so that's another interesting application that we're looking at. And also we're looking at how we can take different, again, macro-scale water balance models, in particular VIC, the WRF Hydro framework, and WBM Plus, and comparing how these guys do in different scenarios with the same data, essentially. And so with that, I've rushed through the last couple of slides, but that's it for me. So I'm going to go ahead and pass it on to the guys at BYU.
Thank you, Joseph. My name is Nathan Swain, and like you said, I'm here at BYU. I'm a doctoral student, and I'm here with my associate, Alan Snow, who is a master's student. And we want to tell you a little bit about some of the work we've been doing with cyber infrastructure and app development using Tesys platform, which is something that I've developed as part of my dissertation. Now, Tesys platform, the goal that we really had was to lower the barrier for water resources engineers and scientists to be able to create web apps. And we see it as kind of an effective medium of sharing models and data in an easy-to-use format that many people are familiar with. And I think a lot of these apps could be used in various aspects of NFIE, especially in the response area. I think they make great interfaces for a lot of the response tools. So the way that we lower the barrier is Tesys platform provides two things. It provides a software suite to address kind of some of the unique functionality that is required by these web apps, and it also provides a Python software development kit. So I'll just explain each of those briefly. The software suite is composed of several open source software to address things like spatial data needs. We have a pretty good web GIS stack that includes GeoServer, 52 North, PostGIS for storing, publishing, manipulating spatial data. We're including things like Google Earth and open layers and high charts for visualizing these types of data in very interactive formats that you've come to expect when you're on a website. And we've also got software like HT Condor and some other things that we've developed in-house that help to coordinate high cloud computing. So a lot of these apps need pretty heavy computational resources. So we've tied that into it. And then we're tying into services like CCAN instances, like data.gov or HydroShare to store file data sets. So that's kind of the software suite, and we tie it all together with a Python software development kit so that you can easily incorporate whatever functionality you need in your app using Python, which has become a pretty popular scripting language. Now I'm going to turn the time over to Alan, and he'll tell you a little bit about the app that he's developed, and really it's an example of things that we plan to do as part of our NFIE proposal.
All right, thanks, Nathan. As you said, my name is Alan Snow. So in my app, what it's doing is taking these forecasts, which are being created by the European Center for Medium Range Weather Forecasts, and it's routing them using Rapid, and then it creates an interface for users to view it. So this slide here is showing you the different processes, which is very similar to what WRF Hydro is doing, and it's incorporating the different atmospheric processes to get temperature and rainfall, and it also has a scheme for the land surface to be able to incorporate the rainfall and then be able to calculate the runoff. When they perform these calculations, they create a NetCDF prediction file, which is global. It covers the entire world, and it predicts what the runoff is going to be 15 days ahead. And they do this in an ensemble nature. So in order to take these forecasts that they have and take it from a grid and to put it into a catchment, we use different data sets that have been created for the catchments, like the NHD Plus or the HydroSheds network to get the watershed boundaries in the stream network. And then using tools developed by Esri, we're able to get the volume of runoff for each specific catch base and downscale it, and then get that in a time series which is compatible for Rapid. So because there's 52 forecasts, this can be pretty computationally intensive and can take quite a while. So I've been doing some research here. I'm working with Scott Christensen. He's doing a lot of things to add the compute functionality into Tesys. And so what I've set up here is in the Amazon cloud, it distributes the computations to different computing nodes. And so it's able to, on each node, it downscales and runs Rapid for that forecast, and then we get the output a lot faster. So the way I have it set up is I have a Tesys app, and I also have a computing cloud that I need to be able to interact and have the data so it's able to be transferred from the Amazon cloud to the Tesys framework to visualize the data. And so in order to do this, I just use a data store, such as HydroShare or CCAN, and the Amazon cloud transfers it up there, and then the Tesys app is able to use that data to visualize it. Then this is the visualization tool using open layers in Nathan's Tesys framework, and here it's able to display the stream network, and it allows the user to click on the stream network and view the projected forecast for what it will be in that stream network. So with this type of a setup, you can take the ECMW forecast, WRF Hydro, or if you have some other forecast method, you could take that. Or you don't even have to have Rapid. You could use a different method to produce your own predictions for what will be in there. And it's a method where you'll be able to either use the output from this app or a similar app and be able to use that in your analysis, or you could create an app which would be able to display data and make it useful so the user will be able to see what the predicted forecasts are going to be.
So to wrap up, really our proposal is kind of twofold. One is we propose to build several apps that make use of the NFIE data sets and data sources with kind of a flooding aim. And we also would like to provide our services for others who would like to use Tesys platform in their projects. And we can do that in a number of ways, by either teaching a short course or providing technical support, even infrastructure like Tesys servers for hosting the finished products. So that is really our stuff here at BYU. We just released version 1 of Tesys last week. So you can get on our site, tesys.ciwater.org, and check it out. Thank you.
Hi everyone, my name is Cassandra Fagan. I'm here at the University of Texas, and today I'll be presenting my project titled NFIE Response, and I'm also working with Madeline Merck, who is at Utah State University, and I'll be presenting her part today because she's under the weather, unfortunately. So as the title indicates, our focus will be on the NFIE response portion of the NFIE conceptual framework. And within this framework, NFIE response has two portions: the planning phase, which identifies vulnerable people, infrastructure, and roads, as well as the action phase that uses flood forecast and flood inundation mapping to indicate zones of risk. And although we recognize that all portions of the NFIE will be feeding into NFIE response, we're mostly going to be using the NFIE River outputs for our project. So we'll be taking the ensemble flood forecasts and the real-time inundation maps and water surface elevations to use that to direct our emergency vehicles and then also identify the vulnerable infrastructure. So we begin our project by producing the NFIE Geo database maps for the two counties we'll be focusing on. I'll be doing my research for Travis County in Texas, and Madeline will be working on Cache County in Utah. So at this point, the NFIE database consists of subwatersheds, catchments, NHG plus flow lines, stream gauges, and dams, and we're looking to add some other components to construct the NFIE response database. So as you can see, there's a lot going on this map. We have added some portions of the map that will help us to assess vulnerabilities. This includes locations of home addresses, roads, various census data, and the FEMA floodplain layer that's been discussed earlier. So if you zoom in to one of the layers, you can start seeing where they intersect and some important pieces. So one of the main aspects of the project is inundation areas during flood events using the NFIE River and assessing vulnerabilities for the planning phase. And most of we have intersected the roads and rivers and extracted the intersections as points. And so this low water crossing indicated on the map is actually the Fritz Hughes Park low water crossing in Austin, Texas. And this low water crossing floods frequently, and this past October, an Austin police deputy actually lost her life on this crossing while checking this vulnerable community that's cut off. So this is the only entrance and exit into that community. So it's cases like this that this project is going to strive to prevent through NFIE response. So this is another example of where the flood layer and roads and address points have been intersected with the FEMA floodplain. So you can see the vulnerable streets in red and the vulnerable address points are in yellow. And you can also notice that some communities may not lie in the floodplain, but they're still considered vulnerable communities because the only means of egress are through the floodplain. So what we're hoping to do in this project is using LiDAR data in both Austin and Logan
to find the street elevations to enough resolution that we can compare that to the water surface elevations that's going to be the output of the NFIE River. So some of the end goals of our project is finding a way to actually map flooded roads and be able to compare what we can actually do in Austin or rather in Travis County and in Cache County with the different data points that we have. And also to compare what emergency response personnel need in the two counties, because they're very different climates, different topography, so they might have different types of flood events. For example, Austin has a lot of flash flooding, and Cache County might have a different, more long-term kind of flooding. So if so, we'll be talking to emergency responders and actually seeing what kind of data they want and what would be helpful and improve their response. And so for our final goal, we'd really like to construct some kind of online tool or app that you could use and view the NFIE response database and turn on and off layers for inundation maps, return periods, and also for various census data and stuff like that. So I think that concludes my NFIE response project.
Okay. So thank you very much. So yeah, those are about, we just heard from 3 different student groups working on different projects related to NFIE. And again, in the NFIE framework, there's a lot of different areas where people can contribute because I mean, there are a lot of assumptions that are being made at different points. So, we encourage people to participate and, and contribute to the different areas the framework has outlined and help us, produce better products and, just keep making things better. So, I don't know, I guess we're happy to take any questions now that anyone has. The next webinar will be on Wednesday, March 4th at 3 p.m. Eastern Time, and we're going to hear about the Iowa Flood Information System.
All right, great. Thanks, Fernando. So if anyone does have any questions at this time, please go ahead and type them into the chat box, and we will relay them back and hopefully answer them for you. So we'll give you a few moments to type those questions in. And just as kind of a recap, there is updated information on the Quasi website regarding the new program categories for the NFIE Summer Institute, and there will be an updated application form being posted shortly as well. So that link again is www.quasi.org/NFIE, and that's where you can find the NFIE program information, the application information, the archived webinars that have been presented during the series, and some additional resources as well.
You are no longer muted.
I'll ask a quick question for Nathan and Alan. Using Tesys, how easy is it to connect the spatial features to time series? Is it typically done through like a shapefile? Like if I had, let's say, 6 gauges and in the shapefile I had links to, let's say, water-mill time series, would that be enough to stand up an app in Tesys, or would something else have to be done?
That would actually be exactly what you would need. So within the app, there's currently what I'm actually using is KML files, which have attributes which are able to give me information about the stream ID, and then I use that information from that attribute to query the site or the server to be able to get the information I need from that server. So you could create a KML file that has attributes which have, or a shape file, which you could actually put on GeoServer. And we're actually working on implementing that into the app as well, where you could actually load a shapefile onto Jira server and query that as well. So if you have that information and you have a backend or another server you want to query with the information you need into that shapefile, that would be all that you would need. Did that answer your question?
Yeah, thank you.
This is David Maben speaking. Could I ask a question of Emily Reed? I was interested in this team science thing, Emily, and I wondered if there's some kind of a mechanism for being able to map out who's connected with who, you know, sort of see a spatial map of all the people connections. That just seems like an interesting thing. Is that something that you've seen before or worked on?
So David, this is actually Emily Clark, and Emily Reed had to jump off to go to another call. She's actually on the line anymore, unfortunately.
Well, okay. I guess I'm not going to get that question answered then.
But we are going to work with Emily Reed from now until the Summer Institute to employ some of the team science strategies so that we can, make the experience for all the participants as best as possible. It seems like they had a lot of success with their Guion fellowship a year ago, so I think she's going to be really helpful in facilitating our participants, or facilitating, good work, I suppose, with our participants.
I'd like to ask a question of Joseph Gutenson. You pointed out the lack of, consistency in the terrain and bathymetry data. What can be done about that? Can we propose something as part of the NFIE to get better information?
Well, that's actually, Dr. Maven, that's what I'm looking into myself, specifically in the bathymetry. My portion of the project, or my project that I've kind of been looking at, if I can zoom back here for you, I kind of had to run over it because just like my advisor, I have a tendency to talk on one slide for 10 minutes. Let's see, where is he? So I happened to find out about these power functions that have been fairly well developed over the past 60 years. They've been questioned a little bit in the past couple of years, but basically they relate both flow and drainage area to the width and depth of a stream. And so what I'm hoping to do is, at least on a statewide scale here in Alabama, is to apply these power functions to the different streams based on basically the power functions are correlated with the different physiographic regions in each particular state. And so I'm hoping to take a look at that, correlate the NFIE, not NFIE, but the NHD flow lines with the physiographic regions, employ the power functions, and look at if I can estimate width and depth and cross-sectional area fairly well. So that's what I'm particularly interested in. As far as topographic information, the LiDAR at this point is great, and I think you also probably know a lot about the blue-green LiDAR, a lot more than I do, which is used for bathymetric measurement as well. So does that answer your question?
Yeah, I want to suggest that one of the things we ought to advance as part of the NFIE is a increased emphasis on precise terrain measurement and bathymetry measurement and the conjunction of the two. And one thing that's really struck me is 5 years ago I asked why couldn't we have a single topographic bathymetric surface at the nation's coastline? And I was assured it was way too difficult to do that and very complicated and so on. Well, a few months ago I saw a lady from the Corps of Engineers, Jennifer Wozencraft, present essentially that. And in the years that have elapsed, 5 years, they developed the new technology that was needed to combine land-based LiDAR and blue-green LiDAR for the coastal waters, and they basically built a single topographic bathymetric surface along the coast. And so if you take the example that you were showing with the inundation pool from the reservoir, it ought to be possible for us to go inland as well from the coast. I mean, if we've out-scienced the coast, we ought to be able to out-science the inland as well. And I think a long-term vision is having a single topographic surface across the whole nation that goes under the water when necessary. And I think one of the things we ought to work towards is, how do we build the technology and how do we define the measurement systems that are needed to achieve that?
Yes, it's very interesting as well because once we have a very well-developed bathymetric data set, we're no longer tied to the cross-sections. We can think of how we do hydraulics completely in a different way. I think there's a lot of really cool stuff that could be achieved with that in mind.
Yeah, let's work on it, Joseph, because there's a colleague, Grady Toole, at Georgia Tech, who's really an expert on blue-green LiDAR, and I think he can help with this. And we should look at exploring some possibilities of new technologies in subsurface water measurement and employing them in the situations like the ones you presented.
That would be great.
All right, well, if there are any more questions, we can take them now. We're approaching 4 o'clock.
Let's just give a pitch for the seminar in 2 weeks' time by Dr. Krajewski, who's the director of the Iowa Flood Information System. They have a fantastic system at the University of Iowa that was developed after the 2008 floods that happened in Iowa. They call it Iowa's Katrina. And they've done some really marvelous things, including precise flood mapping in their cities. They've got a very highly detailed flood forecasting model for their whole state, which is more detailed than NFIE Hydro. They've got a measurement system of about 250 locations across the state of Iowa that includes depth measurement devices that were developed by students at the University of Iowa. So it's really, in a sense, an emblematic system, an example for the nation to follow, and we'll hear about that in 2 weeks' time.
Excellent. All right. Well, thank you, everyone, for being here, and thank you to all of our presenters. And again, feel free to contact me if you have any questions. And we hope to see your applications start coming in for the NFIE Summer Institute.